Hi, welcome to MATH336 lecture on section 2.6 from the textbook. This is the last section we'll be covering in chapter 2. And we're returning to a topic that we looked at before in section 2.4 about mechanical vibrations. And now we're going to look at forced oscillations and resonance. So initially in section 2.4, we only had a zero here on the right-hand side. And we were able to solve those because we knew how to solve homogeneous equations. But from section 2.5, we now know how to solve non-homogeneous equations. So now we can actually look at forced oscillation, where we have some sort of external force on this spring mass system with some damping. So you have a dashpot there, which is providing a damping or like a shock absorber. And we're going to be looking at specifically what happens when the external force is given by a cosine or a sine. So some sort of like periodic force. For example, an earthquake would cause such a external force where it's sort of the ground shakes back and forth at a certain frequency for a certain amount of time, and these oscillations are causing the buildings to sway. And what's interesting is how in some earthquakes you'll see that certain buildings will collapse and other buildings won't. So you could have like very short buildings are okay, very tall buildings are okay, but it's these medium buildings that are collapsing. And this can sort of be explained by what we're looking at here today. So we're going to see what is the effect on the oscillations due to some external force. Okay, so maybe I was going to leave this till later, but maybe I'll read this right now just to give some motivation for what we're doing. So essentially what I want to do here is demonstrate this well-known observation about mathematics, that it seems like it unreasonably is effective at predicting physical phenomena. So it's this unreasonable effectiveness of mathematics to predict physical phenomena, and that's what we're going to see here. We're going to go through, very mathematical arguments, but we'll be able to draw some very meaningful physical conclusions from this. Okay, so let's talk about this. So in this section, we're going to be looking at undamped forced oscillations, and then later on we'll be looking at damped forced oscillations. Okay, so let me read this. So this is on page 165 in the book. It says, in practice, a mechanical system with very little damping can be destroyed by resonance vibrations. A spectacular example can occur when a column of soldiers marches in step over a bridge. Any complicated structure, such as a bridge, has many natural frequencies of vibration. If the frequency of the shoulder's cadence is approximately equal to one of the natural frequencies of the structure, then just as in our simple example of a mass on a spring, resonance will occur. Indeed, the resulting resonance vibrations can be of such large amplitude that the bridge will collapse. This has actually happened. For example, the collapse of the Boughton Bridge near Manchester, England in 1831. And it is the reason for the now standard practice of breaking cadence when crossing a bridge. Resonance may have been involved in the 1981 Kansas City disaster in which a hotel balcony collapsed with dancers on it. The collapse of a building in an earthquake is sometimes due to resonance vibrations caused by the ground oscillating at one of the natural frequencies of the structure. This happened to many buildings in the Mexico City earthquake of September 19th, 1985. On occasion, an airplane has crashed because of resonant wing oscillations caused by vibrations of the engines. It is reported that some of the first commercial jet aircraft, the natural frequency of the vertical vibrations of the airplane during turbulence was almost exactly that of the mass spring system consisting of the pilot's head and the spine. Resonance occurred, causing pilots to have difficulty reading the instruments. Large modern commercial jets have different natural frequencies so that this resonance problem no longer occurs. Okay, so that's kind of to motivate us in this study. So we're going to be directly applying the mathematics from the previous sections, in particular section, the previous section 2.5. We'll apply that and we will draw some very interesting conclusions here about the phenomenon of resonance. Okay, so let's get started. So undamped forced oscillations. So let's apply the material from previous sections in this chapter to study this equation here, where we have a mass spring system without any damping. So there's no friction or anything. So no dashpot or shock absorber. And we'll apply an external force. And we'll just look at this example. So here we have our mass spring system, and then the external force is given by this 5 sine 3t. So 5 is like the magnitude or the amplitude, I guess, of the external force, and this this three is sort of indicating what the frequency of it is. Okay, so let's get started, and we're actually going to start with the system at rest. So it's going to be started at 0 with 0 velocity. So normally without forced oscillations, then nothing would happen. But because we have an external force, you'll see that we're actually going to have some movement from this system, even though we started at rest with no, even though we started at rest. Okay, so let's go ahead and do what we know how to do. So first of all, we're going to look at the homogeneous equation, and we're going to find the general solution for that. So we would write down our characteristic equation, and we would solve it, and we would get R is equal to plus or minus I times 2. And so therefore, what's it called? I forget what it is called. Anyway, it'll come to me in a second. This is our general solution for the homogeneous equation. I keep thinking companion solution, but that's not the right word. Okay, so there's our solution for that. Okay, and now we need a particular solution. So what is our external function? It is 5 sine 3t. And if we take derivatives of this, then we're given, let's see, 15 cosine 3t, and we take a derivative again, and we'll get sine again. So we'll get negative 45 sine 3t, and so on. So we see that the only terms that are really showing up here are going to be this, this sine. So there's one term, and cosine. And it's 3t, right? Oops, I just realized that these need to be, we're using x and t. Okay. So we see that these are not solutions of the homogeneous equation. So we're good. We can take as our phi 1 will be sine 3t, and phi 2 will be cosine 3t. And so therefore the form of our particular solution will be a sine 3t plus b cosine 3t. Okay, so what do we do with this? We substitute it into our differential equation up here, and then we'll determine the values of a and b. So to substitute that in, we need the first derivative. Well, we need the second derivative, in fact. So we start with the first derivative here, and oh, this will be a minus. And then the second derivative will be minus 9a sine 3t minus 9b cosine 3t. Okay, so now we'll substitute those in. So let's grab our differential equation here. Copy that, bring this down here. Oh, well, it didn't. Let me just rewrite it again. So x double prime, oh, I see I'm using y again. So used to using y's. So in this case, we're using x. So x. Okay. So x double prime p plus 4xp is equal to 5 sine 3t. Okay. All right, so let's see. So we'll substitute our stuff in. So we have, first of all, our second derivative right there. And then we have plus 4 times this guy. Copy, paste. Okay. And let's see, we've got this sine here, and we've got cosine here. So let's collect these terms together. So the coefficient of sine is going to be 4a minus 9a. So in total, that gives me minus 5a sine 3t. And then we have minus 9b plus 4b. So that's minus 5b cosine 3t. All right. So therefore, we have negative 5a equals 5. And we have negative 5b is equal to 0. So I'm just matching up the coefficients here. So you can see that negative 5a is equal to 5, and negative 5b is equal to 0 because there's no cosine term over there. So therefore we get a is equal to negative 1 and b is equal to 0. So therefore, the particular solution is going to be negative sine 3t, and that's it. So that's our particular solution, right? Let me just check, make sure that's good. I guess I have xp right there. Yeah, so that's correct. Okay, so therefore, what's our general solution? We have x of t is equal to c1 cosine 3t. Oh, it wasn't 3, it was 2. 2t plus c2 sine 2t minus sine 3t, right? Because we have x is equal to, oh, complementary, that's the word. The complementary solution, I knew I'd remember it. So the complementary solution and then the particular solution. So there's our general solution of the differential equation. And now we use our initial conditions to determine the coefficients, C1 and C2. Okay, so let's put a box around this as well. Okay, and it looks like I need to get some more space here. Okay. So what do we need? So we're going to use our initial conditions. So x of 0 equals 0 and x prime of 0 equals 0. So we need to take the derivative of this. Negative 2 c1 sine 2t plus 2 c2 cosine 2t minus 3 cosine 3t. Okay, so let's start with x of 0 equals 0, and what do we get? This will be c1 times cos of 0, which is 1, plus c2 times sine of 0, which is 0, and then minus sine of 0, which is 0, and that equals 0. Okay, so that will tell us that c1 is 0. And now let's do x prime of 0, and we'll get negative 2c1 times 0 plus 2c2 times 1 minus 3 times 1 equals 0. Okay, so therefore we have c1 is equal to 0, and c2 is going to be 3 divided by 2, right? So if I move this 3 over here, and then I have 2c2 is equal to 3, and then I divide both sides by 3. Oops. Yeah. Okay, so there's our coefficients. And so therefore, what do we get? We have x of t is equal to 3 over 2 sine 2t minus, and I already forget what that term was. Oh, it's just minus sine 3t. All right, great. Maybe we could plot this. It would be interesting to see what does this function look like. So what do the oscillations now look like? You can see that there's some oscillations coming from the natural frequency of the system. So this 2 here is the natural frequency. I think it's the circular frequency, right? It's the radians per second. And then there's another frequency showing up here as well, which is coming from the external force. So it's kind of like a combination of the natural frequency of the system and the frequency of the external force. So it would be interesting to see what this function looks like when we plot it. So I'm going to pull up my plotting software and we will plot it. Okay, so here we are in Julia and we want to plot this function. So let's just type it in. So we have 3 divided by 2 times sine of 2t minus sine of 3t. All right, and let's just check that if I do x of 0, I get 0. Okay, so that's good. I don't have the derivative typed in. There is some software that will let you do automatic differentiation of functions like this, but let's not worry about that. What we're really interested in doing is plotting this. So let's load up the plotting package in Julia. And this can sometimes take some time, so I'm going to pause. Okay, all loaded up. So now we want to plot this function. So what do we want? We want to plot this function x from like 0 to, I don't know, let's do like 4 pi, I guess. I'm not sure how many, what length I want to plot this at, but let's just try this. Plot it from 0 to 4 pi. Okay, and here it is. Let me blow this up nice and big. So there's the graph of that function. Oh, it's labeled as y1, but let me change that. So I want to say label equals like x of t. Right? Maybe x label is t, and the y label is x. Okay. There. So we got the x-axis and y-axis labeled properly. So there's our function x of t, and you can see that it definitely has 0 velocity initially. So what sets this mass in motion is this external force. And you can see the effect of having these two together. And what you get is the sum of these things are actually periodic. So this is looking nice. I wonder, maybe I could change these ticks down here. Let me just see. I'm going to try to change those ticks so that instead of indicating the integers, I'll have it indicate the like pi and 2 pi and so on. So let me try that. Okay, well, I gave up on fixing these tick marks here, but I did export the image and I put it inside of the notes. So there, we have it inside of our notes now. Yeah, I wasn't able to get it, but you can kind of see that this is around, this is pi, this is 2 pi, and so on. So I just wanted to get it to line up nicely here like that. Oh, well. So there we have it. So there's the resulting oscillations of the system. So very interesting. And one thing maybe we're interested in is what is the period of this? So the period looks like it's this. So it looks like it is 2 pi. And what is that? How can you determine that mathematically? Well, the way that we could determine it is by looking at the period of these two functions here. So let's see. The period of sine 2t. Okay, so first of all, the period of sine of t is 2 pi. So so the period of sine of 2t, so that's twice as fast. So it's when 2t is equal to pi. So that's when t is equal to pi. So the period of this is going to be pi. And the period of sine of 3t is by the same argument, it's when 3t is equal to 2 pi. So 3t equals 2 pi, that's when t is 2 pi over 3. So then what is the period of x of t? The period of x of t is the least common multiple of pi and 2 pi over 3, which is, so what's the least common multiple? So we have pi, 2 pi, 3 pi, 4 pi, and so on. Those are the multiples of pi. So integer multiples. I'm thinking just integer multiples. And then for 2 pi over 3, the let me see, the least common multiple, or sorry, the multiples are 2/3 pi, and then 4/3 pi, and then 6/3 pi, which is 2 pi. So it looks like the first time that they both line up is going to be 2 pi. Oops, 2 pi. So that is the period, and that's what we noticed when we plotted it as well. Okay, so there we have it. I guess another thing that would have been nice to plot here is to plot those separate functions, the sine 2t and the sine 3t as well, just to kind of see how they line up. But yeah, there it is. So let's finish there and move on to the next section. So now we're going to talk about resonance. So resonance is when we see the magnitude of the oscillations is getting larger and larger due to this external force. Kind of like when I was talking about the soldiers marching on the bridge, if their cadence frequency matches one of the natural frequencies of the bridge, then this can cause the bridge to collapse. So let's see if we can observe this phenomenon mathematically using what we know about solving differential equations. So for the spring mass system, we have, so again, we're just looking at undamped oscillations still. So there's no damping term. So this is just a mass and a spring and then an external force. And we're going to use cosine of this. So okay, so the natural frequency of this is, so where does that come from? It comes from looking at the homogeneous equation. And then you write down its characteristic equation. And the roots are going to be equal to plus or minus I square root of k divided by m. Okay, so that's where this natural frequency is coming from here. It's the frequency of the oscillations due to the mass spring dynamics. Okay, so and then of course we know that the solution of this homogeneous equation is therefore given by this, where instead of writing this all the time, we're just going to use omega naught here, which is the circular frequency. Okay, so that's the natural frequency of the system. So if you were to just like not have an external force and just set the system in motion, then it's going to oscillate at this circular frequency. Okay, so now what is the effect of this external force that has a frequency, a circular frequency of omega? Well, we'll start with two different cases. So first case is if omega is not equal to omega naught. So if the external frequency, the frequency of the external force is different from the natural frequency, then what is the form of the particular solution? So we know from last section that the form of the particular solution are going to be all the terms that appear in the derivatives of in f and the derivatives of f. So that's going to be cosine omega t and sine omega t. And since omega is different than omega naught, these terms here are not solutions of this homogeneous equation. Okay, so let's continue. So now we want to determine this a and the b. So we take the first derivative, we take the second derivative, and then we substitute those into the differential equation. So there's our differential equation right there. And we substitute them in. So here's the x double prime p, and this is the xp. And we rearrange the terms. So I'm going to collect all the cosine terms and sine terms together. So we have minus m a omega squared in front of that cosine, and then in front of this cosine we have a times k. So I just factored the a out because that's the common term, and then we're left with this. And similarly for the sine term. Okay, so therefore this coefficient is equal to f naught, and this coefficient is equal to 0 because the coefficient of sine omega on the right hand side is 0. So we have this and this. Then we divide both sides by this k minus m omega squared, like that. And then same here when we get b is equal to 0. So there's our a. Now, recall that omega naught is given by this, and so we actually have this term here. Wait a second, did I do something? Yeah, no, that's right, that's right. Yeah, if you square both sides of this, then you get omega naught squared is equal to k over m, and then you multiply the m over here, and we get this. Okay, so now we have this equation, which lets us substitute this k with m omega naught squared. And when we do that, we end up getting this, and then we can factor out this m and put it up in the denominator like that. Okay, so this is sort of the key observation right here that we needed. So this is telling us something very interesting, which we'll see in a second. So here is the particular solution of our differential equation, and then that allows us to get our general solution. And of course, the C1 and the C2 depend on the initial conditions. But what's very interesting here is we have some kind of motion that depends on this external force. So it's the frequency is omega, and this is the amplitude of this vibration. So it is possible that this amplitude could be quite large, in fact, and large amplitude, of course, is bad news, because that's when structures fall apart, when they're oscillating at a very large magnitude. That's when things can no longer keep standing, like a bridge or a building when there's an earthquake. And in particular, notice what happens is if this external force is approaching the natural frequency, then this amplitude is actually going to approach, it's going to be as large as you like, right? So the closer you get to omega naught, what's happening is this denominator is going to 0. And when you divide by smaller and smaller numbers, you're getting larger and larger numbers. So this thing is going to go to plus infinity. I mean, it'll never be like, plus infinity, but it's but it just tells you, like, as you get closer and closer to the natural frequency, bad things will happen. And that's why when the soldiers are marching across the bridge, if their frequency of their march is very close to one of the natural frequencies of the bridge, then we can start to see a very large amplitude in the oscillations of the bridge due to the marching of the soldiers. So this is the frequency the soldiers are marching at, and this is the natural frequency of the bridge itself, or one of the natural frequencies of the bridge. So because large structures have like a lot of different natural frequencies. Okay, so remember, we're just doing this in the undamped case. We're assuming that there's no damping, and so that is obviously affecting what we're getting here. But it is showing a very interesting phenomenon. So the amplitude of the oscillations can increase without bound as the external frequency is approaching the natural frequency. Okay, now what happens if we're actually equal? Then we have a different solution to the differential equation. In that case, the form of the particular solution has to have an extra t added here to these two terms, because these terms themselves are solutions of the homogeneous equation. So in order to get two linearly independent terms that are not solutions of the homogeneous equation, we multiply by t. Okay, so let's now take some derivatives. So we get the first derivative here using the product rule. I won't go through all the details. And then we take the second derivative here, again using product rule. And then we collect the terms together. So there's a lot of terms that are showing up here, but I'm going to collect all the cosine terms together. So we have this coefficient of cosine, and then there's actually two of these. So we get 2b omega w. And then similarly for the coefficient of sine omega naught t. Okay. Now we substitute those expressions into our differential equation, and we get this. So this is the full differential equation with those terms substituted in. And we have this. I mean, it's quite a mess, but let's simplify it a bit. So let's rearrange the terms. So we'll collect the cosine terms together, and we'll collect the sine terms together. And we end up getting this expression. Okay, so it still looks like quite a mess. So let's see if we can simplify this further. Let's see. So this is the key idea, is that since omega naught is equal to this, then this is actually equal to 0. Now, does that term appear up here? We have m omega naught squared. And then, so it's minus m a omega naught squared. And then we have plus a k t. Oh, and there's a t there. So yeah, so there's this term here. So maybe I'll highlight what this tells us. So it tells us that this term and this term cancel. And it also says that this and this will cancel. Okay, so that's what that is implying. So we get a much simpler form now of our equation. So all that stuff goes away, and we're just left with this. And then we can equate the coefficients. So this will be equal to F naught, and this will be equal to 0 because there's no sine terms over here. So there we have our equation. We solve for B, we get this, and we solve for A, and we get that. And therefore, here's the form of our particular solution. And now look at what the amplitude is of the oscillations. So this is the amplitude. So there's the sine wave. So the sine wave just has amplitude plus, has amplitude 1. But when you multiply it by this term, we get this as being the amplitude of this particular solution. So let's put all this together in our solution of our differential equation. And here we see this amplitude of the oscillations is here. I guess these two terms could actually be combined together. So I could have done that, but that's fine. This is still, so actually like the oscillations of this are going to be this plus whatever this C2 is. But what's interesting about this now is it's telling us that not only is the amplitude when the external frequency is the same as the natural frequency, then the amplitude of these oscillations is actually increasing with time. So as time goes on, we're going to be getting larger and larger oscillations when the external frequency is exactly equal to the natural frequency. And this is the phenomenon known as resonance. It's like the external frequency is, it's like pushing a child on a swing. And if you sort of keep pushing at the same frequency, then you can have the child go, higher and higher. But if your pushes are at the wrong time, then that'll cause the person to swing, slower and slower. So that's kind of what's going on here is the external force is like pushing at exactly the same frequency as the natural frequency. And this is just adding more and more amplitude to the oscillations. So here I've plotted the slope, or this line which represents the oscillations, the magnitude of the amplitude of the oscillations. So right here, and it can be plus or minus. So I put it there. And then we have our oscillations, which are going to match this slope at a certain time. So like whenever this is. Okay, so that's the idea. And you can see that if something is oscillating like this and getting like larger and larger oscillations, then obviously this is really bad news for whatever structure is going through this. Eventually the amplitude of these oscillations is going to be so much that the structure will fall apart. Okay. So let's see, is there anything else? Okay, that's it. Oh, and yeah, we already read this stuff. So that's the story about how this occurs. We've seen examples of this occurring. Okay. So let's look at maybe an example that's familiar to you, having a washing machine that is oscillating. I just had this today. We were doing some laundry downstairs. I don't have a front-loading washing machine. I have a top-loading one, but the thing that was inside of it was on one side, and so as it was spinning, it was causing the washing machine to move across the floor. So the washing machine started like walking across the floor. And I got there just in time before it unplugged itself from the wall. So let's look at a situation like this where you have a front-loading washing machine. So we have, as it's spinning, it's going to be providing some up and down motion at a certain frequency. And if that washing machine is mounted on a thick rubber pad, then that thick rubber pad can act like a spring. And so this could cause this resonance to occur in the situation if the machine is spinning at a certain frequency. So, so we'll have to use the fact that the weight of the machine on the rubber pad is depressing it by 0.5 centimeters. And its rotor will spin at omega radians per second, exerting a vertical force of this amount. So we don't know what the amplitude is. This could really be anything. It could be small or it could be large. But no matter what this is, we're going to see that resonance vibrations will occur at some speed. So as the speed is getting higher and higher, eventually we'll get to a speed that matches the natural frequency of the of this washing machine on this rubber pad, and we're going to get some resonance occurring. And we're going to neglect friction in this case, which is probably a little bit unreasonable, but I don't know what kind of friction could occur. Definitely not air resistance is not going to play a huge factor, but anyway. So let's figure out what this when this resonance will occur. All right, so we have to use the information we're given to determine the spring coefficient. So what is the spring coefficient? It says that the force that's given by the spring is equal to minus k times the displacement. And then we can figure out what this k is. So the displacement in this case is going to be equal to, well, maybe let's talk about the force first. So the force is equal to the weight, right? So it's the mass, it's the mass times gravity, which is 9.8, and it's in the negative direction. So, oh wait, but the force will be pushing up, right? So, oh wait, no, let's see. So yeah, this is a force pushing down on the spring, and so the spring will push up at exactly the same force. So we do have m times g on the left, and on the right we have negative k, and then the displacement is negative, let's see, I forget if I put this whole thing into meters. I think that's what I do. Yeah, let's write it in terms of meters. So it'll be negative 0.005, right? Half a centimeter. Okay, so there's the displacement, and so therefore we solve for k. So k will be equal to m times g, which is 9.8, divided by 0.005. So what is that? I guess I have it written down here. So that is going to be 1960 times m, the mass, right? So m is the mass. It's not, that's not meters. It's not 1960 meters. So let's just verify this. 9.8 divided by 0.005. Yeah, that's it. Okay, so there's our spring coefficient. And now that we have this, we can determine the natural frequency. So the natural frequency is given by the square root of k divided by m. And so we're going to get 1960 times m, which is the spring coefficient, divided by m. And now these two m's will cancel. And we're just left with the square root of 1960. Okay, square root of 1960. So that's about 44. Well, I mean, maybe you want to know what it is. So I have this written down here. It's 14 root 10. Yeah, 14 times the square root of 10. Yeah. And so therefore, omega naught is going to be like 44.27 and so on, radians per second. All right. So that's the natural frequency. And then we want to get this in hertz. So to get this in hertz, we would have, let's see. So this is going to be, so what is this in hertz? So we need to convert this into cycles per second. And how many radians are there in a cycle? There's 2 pi radians in a cycle. So this is going to be equal to 44. Well, let me write it down here as exactly this. So that's radians per second. And then we want to multiply by cycles per radian. And this will give us the answer in terms of cycles per second, which is also known as hertz. Okay, so what is that? So I'm going to divide by 2 pi. And I get, it's approximately 7.05. So this will be 7.046 and so on hertz. So that's the natural frequency of the system. So therefore, resonance vibrations will occur at about 7.046 hertz. Okay, so there you have it. So if you run the washing machine and have it spin at approximately 7.04, about 7 spins per second, right? So about 7 spins per second, and you're going to start observing resonance vibrations in this washing machine on a rubber mounted pad, mounted on a rubber pad. Okay. Okay, so of course it's a little bit unreasonable to assume that there's no damping that is occurring, because we always have some kind of damping. Otherwise, things would just vibrate on their own forever, which is obviously not a reasonable thing to assume. So so let's look at what happens when we have some damped force oscillations. So we'll do this example here where now we have a damping coefficient, and here is the external force, and we're going to start it at rest. So we want to find two parts of this solution. So the solution is going to have one part which is going to represent a steady periodic solution, and this is going to be at the natural frequency of the system. And then there's going to be a transient solution as well. And this solution will be approaching 0 as t goes to infinity because of this exponential term. Okay, so initially this is going to cause, we're going to see something occurring here, but then as time goes on, this will go to 0 due to the damping, and then we're going to arrive at this steady periodic solution. And we'll plot these. We'll plot these out. In particular, we'll plot this, and then we'll plot the solution, and you'll see how this solution here will be approaching the steady periodic solution as time goes on. Okay, so let's solve this equation. So what is our equation? Here it is. Let me just grab this. Just put it over there. Okay, so we have our homogeneous equation. So we write down our characteristic equation. Okay, so let's solve this. I guess the easiest way is to use the quadratic formula. So -6 plus or minus the square root of 6 squared minus 4 times 1 times 13 divided by 2 times 1. Okay, oh, what is that doing down there? Do I have it up? I thought I had it up there. Yeah, I do. For some reason it added it twice, so I'm gonna delete that. Okay, all right, good. All right, perfect. So what is this? Let's see. 36 minus 4 times 13 minus 16. Okay, so that's going to be -6 plus or minus square root of -16 over 2. So therefore, r is equal to -6 plus or minus I times 4 divided by 2, and that gives us -3 plus or minus I times 4. So those are the roots of our characteristic equation. And so therefore the complementary solution is going to be given by C1 e to the -3t times cosine 4t, right? So this 4 is giving us this number here, and the -3 is going up here in the exponential. And then we have plus C2 e to the -3t sine 4t. Okay, so there's our complementary solution. All right, so now we have that. Now we can go ahead and find our particular solution. So let's look at this now. Okay, so what is so our function is equal to this, and when I take the derivative, I'll get 50 cosine 5t, And if I keep taking derivatives, I'm just going to keep getting like sine 5t and cosine 5t. So those are the only two terms that are going to appear in the function and its derivatives. And so therefore, we get phi 1 is equal to sine 5t, and phi 2 is equal to cosine 5t. And also, of course, I'm checking that are these solutions of this? And the answer is no, because we have 5 here and there's 4 here. So we're good. So those are the functions that will comprise our particular solution. So xp is going to be a times sine 5t plus b times cosine 5t. Okay, so we have to solve for the a and the b. So let's take some derivatives. 5a cosine 5t plus, minus 5b sine 5t, and then negative 25a sine 5t minus 25b cosine 5t. Okay, so we have our derivatives. Now let's substitute those into our differential equation. Okay, so the particular solution has to satisfy this differential equation, so we'll make these substitutions. So we have this plus 6 times this plus 13 times this guy. And that's equal to 10 sine 5t. Okay, so let's highlight the terms that we're interested in. So sine here, here, and here. And then we have cosine here, here, and here. So that means that when we collect all the sine terms together, we'll have negative 25a. Oh, but there's actually going to be negative 25a plus 13a. So those will simplify. So what is that? Is that like negative 12, right? When I add 13 to negative 25. Boy, I feel like I want to check that just to be sure. I don't want to make a mistake here. Yeah, negative 12. Okay, that's what I thought. Okay, so sine, a, and then minus 5b sine 5t, and then plus, same thing for cosine, we have negative 12b. Oh, this is not 5. I missed the 6, so this is actually 30. 30 plus 30a. Cosine 5t. Okay, let me just stop for a second and verify this. Let's see. Yeah, negative 12a minus 30b, yeah, and negative 12b plus 30a. Okay, I think that's good. Okay. Okay. So therefore, we have negative 12a minus 30b is equal to 10. And we have 30a minus 12b is equal to 0. So there's our linear system. And maybe this looks like it's going to be quite the headache to solve by sort of solving for one variable and substituting into the other equation. So why don't we try using Cramer's rule for this? I think Cramer's rule is going to make our lives easier. So let's do Cramer's rule. So what does Cramer's rule say? It says that A will be equal to the determinant of this matrix divided by the determinant of this matrix. Okay, so what do we get? We get negative 120 divided by 144 plus 900. Okay, what is that? 120 over 1 over 1044. 10 over 87. Okay, and then B is equal to the determinant of negative 12, 30, 10, 0. So this time we get negative 300 over, and then we know already this is 1044. Okay, so 300. 25 over 87. Okay, so there's our A and our B values using Cramer's rule. And I suppose it would be good to actually just quickly verify that these are correct. So I'm going to do this quickly in Julia. Let's see, B is equal to this. And then I just want to check minus 12A minus 30B, 10. And then 30A minus 12B, 0. Perfect. Okay, so I do have the correct solution. So I think that was a lot easier to do it this way. So there's our solution. So now what does that tell us? Okay, so here is the particular solution. Let's bring that down here. So oh, I missed the, there we go. Okay, so therefore xp is equal to negative 10 over 87 sine 5t plus 25 over 87 cosine 5t. All right. So there is our particular solution. And I think we're going to want to write this in sort of the standard form. So we'll do that in a sec. But I just want to point out, this is actually going to give us our steady periodic solution, because this will actually continue forever. Whereas the complementary part, this part here, so as t goes to infinity, these exponential terms are going to go to 0. Okay, so before we add these two terms together, let's simplify this xp by writing it in a standard form. But maybe I'll just point out quickly. So this is going to be our steady periodic. steady periodic what? What did I call it? Steady periodic solution. Steady periodic solution. So that's our steady periodic solution, and this is going to be our transient solution. Although we don't know what the C1 and the C2 are yet. We need to use our initial conditions to determine that. Okay. I don't know, maybe we should do that first. Why don't we do that first? I guess it won't be too bad. So let's put everything together and determine those solutions. I think, yeah, let's do that. Let's do that. Okay, so therefore, x of t is equal to, and I'm going to take this exponential out, c1 cosine, was it 4? Yeah, 4. Okay. 4t plus c2 sine 4t as well. And then we have this, I'm just going to write xp here. I'll just write xp. Okay, and I'll take the derivative. So I need to do a product rule here. Ooh, I'm going to run out of space. Let me move this down here. Yeah, maybe I will just write this out in full. Let me swap. I'll change the order. I'll put the cosine term first. And then I'll put the sine term second. Okay. Then minus 3 e to the negative 3t c1 cosine 4t plus c2 sine 4t. And then I need to take the derivative of this stuff, which is going to be negative 125 over 87 sine 5t minus 50 over 87 cosine 5t. Okay, I'll just leave it like that. I guess I could simplify that, but we don't really need that super simplified. So let's just keep it like that. So x of 0 is 0. So what does that tell us? We have e to the negative 3t, which is 1. And then we have c1 times cosine of 0, which is 1, plus c2 times sine of 0, which is 0. And then we have those other terms, plus 25 over 87 times 1, and minus 10 over 87 times 0, and that's equal to 0. Yeah, okay. All right, so now what does this tell us? So therefore, C1 plus 25 over 87 is equal to 0. So therefore, C1 is equal to negative 25 over 87. Okay, so now let's use the other initial condition. So now I want to substitute 0 into this. So I'll get 1 times negative 4c times 0 plus 4c times 1. So I'm just going to put, negative 4c1 times 0 plus 4c2 times 1. And then minus 3 times 1 times c1 times 1 plus c2 times 0. And then minus 125 over 87 times 0 minus 50 over 87 times 1. Okay, and that is all equal to 0. Okay, quite a mess. Let's simplify this. So we have 4c2 minus 3c1 minus 50 over 87 is equal to 0. So therefore c2 is equal to 1 over 4, 50 over 87 plus 3c1. And that is equal to what was c1? Minus 25 over 87. So therefore c2 is equal to what? So I'm going to use my calculator to do this. 1 over 4 times 50 over 87 plus 3 times negative 25 over 87 negative 25 over 348. Okay. So therefore, x of t is equal to what? Let's see. So that was e to the negative 3t times c1, which is negative 25 over 87 cosine 4t minus 25 over 348 times sine 4t. So that's our transient solution. And then we have our steady periodic solution, which is given by this. Oh wait, that's not what I wanted. I need to be more careful. Copy that, that's it, right there. And then paste. Okay, so there it is. However, it's not written in the form that they want. They want it in sort of the standard form. And before I go on, I'm just going to kind of double check everything. What did I do wrong? Oh, I see. I might have made a terrible mistake at some point. Did I make a terrible mistake? I thought everything was okay. Let me just double check. Ah, I did make a terrible mistake. Oh my goodness. This 4 should have been a 2. Wow, that's going to change quite a few things. Okay, let me go through and fix this. and I will be right back. Okay, all fixed. Now I found actually another mistake. So I changed all those 4s to a 2, and then what was my other mistake? It was right here. So I missed this minus sign. So I had to add that minus sign in, which made this a minus sign here, right? So so that was now a minus. And when I take the derivative, I get a plus, and so on. So that minus sign was missing, and so now I have the correct C1, and I have the correct C2. And oh, I forgot to update. Oh no, that's right. Yeah, I think this is all correct now. Yes, yeah. So this is all correct. So we got the right thing here. Okay, perfect. Okay, so therefore the steady periodic solution is SP for steady periodic. So it's going to be this part right here. So that's the steady periodic component. And then this is the transient part. Okay, so the steady periodic solution is this. So let's go ahead and write this in the standard form. So how does this work? Okay, so what we need to do is we need to figure out what the C is. So the C is going to be the square root of A squared plus B squared, where this is the A and this is the B. So let's write that in. Okay, so what is C equal to? So what is that? Let's just check this. So we have 25 over 87 squared plus 10 over 87 squared. That's 25 over 261. So it's the square root of 25 over 261. And that simplifies to 5 over 3 root 29. Okay, we're just going to keep it like that. That's perfectly fine number for C. So there's our C, and now we need to figure out what the alpha is, right? So the alpha is going to depend on, so recall that cosine alpha is equal to A over C, and sine alpha is equal to B over C. And we notice that since B is negative, it's this negative 10 over 87, the sign is going to be negative. And so therefore, we're going to be in the lower half of the unit circle. So the formula that we'll use for alpha, then alpha will be 2 pi minus the inverse cosine of A over C. Okay, so that's because sine of alpha is negative. That's why we use that formula. If sine was positive, then we would use just the cos inverse of A over C. Okay, so let's see, what is this going to be? So C is that, and A is negative 25 over 87. So A divided by C is negative 3. Wait a minute. Oh, I forgot to take the square root. On the computer, I forgot to take the square root. Let me just type it in here. So C is equal to 5 divided by 3 times the square root of 29. Okay, that's better. So now A divided by C. Yeah, I was like minus 3. The number needs to be between minus 1 and 1 in order for us to do the inverse cos. So now I get like minus 0.928. Okay, so that's good. So then 2 pi minus arc cos of A divided by C. So that's about 3.522. So this will be like 3.522 and so on. So it's about that amount. Okay, so there's our alpha. Now I forget, do I call this alpha naught or do I call it alpha 1? So the steady periodic solution, I'm going to use alpha naught. Okay, so that's our alpha naught, and this will be C naught. Okay, so that's, and then this is omega naught. Okay. So this will be alpha naught. So all this is alpha naught, C naught. So this is C naught. Okay, so therefore, the steady periodic solution is going to be this C value, 5 over 3 root 29 times cosine of, and the omega naught is 5. So omega naught is 5. And this is the C naught is right here. Maybe I'll write that up here instead. Well, anyway, so omega naught is 5. So this is coming from here. So omega naught is 5. So we get 5t minus alpha naught. And I'm not going to write that number in exactly, but it's about 3.522. So there's our steady periodic solution. And then we need to do the same thing for the transient solution. So the transient solution is this thing right here. Okay, so let's put this in the standard form. So, so we're using C1 for this. So it's the square root of, a squared plus b squared. And in this case, the a is this and the b is this. So we get the square root of 25 over 87 squared plus 125 over 174 squared. Okay, so let's compute that. 25 over 87 squared plus 125 over 174 squared. Okay, that's 625 over 1044. And that simplifies to 25 over 6 root 29. So there's the C1. And now we have cosine of alpha 1 is equal to A over C1, and sine of alpha 1 is equal to B over C1. And in this case, this is going to be positive. So therefore, alpha 1 is just going to be the arc cos or inverse cos of A over C1. And what do we get when we do that? So A is equal to 25 over 87, and C is 25 divided by 6 times square root of 29. Okay, so then the arc cos of A over C, it's about 1.19. Okay, so that's what that is. Okay, and so therefore, I think we got everything we need now. So there's our alpha 1, we have C1, and omega 1. Omega 1 is the circular frequency, which is 2 radians per second. Okay, so therefore, the transient solution is going to be C1, 25 over 6 root 29 times, I need that exponential term in there too. And then cosine of 2t minus alpha 1. And alpha 1 is given by this. Okay, so there it is. Okay, so now we have our transient solution and we have our steady periodic solution. So let's go ahead and do a plot of these to see how everything looks together. Okay, so here we are. I already typed in the definition for the steady periodic solution right there. And here is the transient solution right there. So I've typed that all in. And notice that here I've defined alpha naught, and here is alpha 1. So these are the values that we have in the notes that we saw. For alpha 0, it's about 3.522, and alpha 1 is about 1.19. Okay, so everything is typed and looks good in here. So now let's see. What do we want to plot? So, we want x of t as well. So x of t will be the steady periodic solution plus the transient solution. So that's what x of t is. And I guess let's plot the steady periodic solution first. And I'm not really sure how far to go into the future here. I wonder, I think this is in the, what do they do in the solutions for number 12? Oh, they go slightly above pi, so maybe like 4. Looks like they go from 0 to 4 seconds. Okay, so let's do that. Okay. So go to like four seconds. And then the label for this is going to be equal to the XSP, so the steady periodic solution. Okay, so let's plot that. Let's see how that goes. Okay. So there it is. There's our steady periodic solution. And now let's see what the, oh, maybe I'll keep this big. Okay, and now we'll add to this plot, we'll add the plot of the function itself. So x from 0 to 4, and the label is going to be x of t. Or maybe I'll just, yeah, well, x of t. I feel like I should have changed that other one then. Yeah, let me do this again. So this will be t. Oh, I should do some x label is t, and the y label is x. Okay, and then we'll do this one. Okay, perfect. Okay, great. Okay, so the red is our slightly reddish orange is the actual solution. And you can see initially it's quite different than the steady periodic solution, but then as you know, after about like a 1.5 seconds or so, then we're basically the same as the steady periodic solution. So initially, the external force on this system, which has circular frequency of 5 radians per second, that effect dies off after a while, right? So the circular frequency of the transient solution, let's see. So, right, yeah, the circular frequency of the transient solution is 2, and the frequency of the steady periodic solution is 5. And actually, so which 5? So we have 5 and 2, right? So 5 is actually the external the frequency of the external force. So it's actually the external force that eventually wins out in terms of the frequency of the motion. And the natural frequency of 2 that eventually dies out. So that's what we get here. Okay, so that's the effect of damping. We have a transient solution, which is the natural frequency that eventually dies out, and we're just left with the steady periodic solution, which has frequency that is equal to the frequency of the external force. Okay, so I'm going to export this and save this figure, and then I'll put it in the notes for you to have a look at. Yeah, so I hope you enjoyed this. Definitely those of you who are in mechanical engineering are going to be seeing a lot more of this and more, probably more interesting structures rather than just a spring mass system. But it's really neat to see how the mathematics we've been studying really gives us this nice physical interpretation and really matches what we would expect to see in reality. So very cool. All right, well, thank you so much for watching, and I will see you in the next video.